some reason it won't start. There we go. Okay. What is it? Almost 2, right? So we're going until 3 o'clock, and then you're going to have the test on the previous chapter, right? So we're going to start on 23.
23.
What's that?
What if we don't finish today?
What if we don't finish what?
The chapter, the last day
Is Thursday, and we got plenty of time to finish this chapter. Yeah, final is Tuesday. Yeah, we're not going to have time for the lab for 23. That's pretty obvious. So what we'll do, okay, and that's what I was going to do. So let's hit that now. Okay, right now we're getting ready to start on chapter 23, weather and climate. We'll go as much as we can in the next 70 minutes, okay, until 3 o'clock. And then we'll stop there, and you'll have the test on chapter, what was it, 20? I believe it was, right? Yeah, chapter 20, Shaping Earth's Surface. No, you've had that, okay? All right. And you didn't like it at all, I could tell. Y'all were griping and complaining. I could hear you. You don't think I can hear, but I can. Okay.
It was one open book.
Just one, yes. You only have one book, so that's the one that's a book. Okay. All right. So what we'll have then we'll have the test on chapter 20, and that'll be it for today. Then on Thursday, we'll continue with chapter 23, and my guess is that we'll probably, I'm pretty sure we'll finish the chapter within the time that we have then. There, like I said, there will be no lab. There's not really time for it, and that's usually the field trip to Channel 13, and we just don't have time for that. Sorry about that. That's always fun. But if we do have some time left over, we'll just cover a little bit, just touch on 24. You won't be tested on it at all for a test, okay? Now, 23 you will, okay. So, okay, that's what I was just getting at. The next Tuesday is your final exam. First day of finals is Tuesday. I guess you could take it either Tuesday or Thursday, but I'm just guessing all of you want to take it, get it over with. Well, I mean, take it because while it's fresh on your mind. Right, yeah, okay. If that's okay, then I think that's when it's scheduled for, is Tuesday. So we'll do that. So your final exam will exist in 2 parts. One is the chapter 23 chapter test, and that'll take probably less than 30 minutes. And the second part will be the comprehensive, which covers all the chapters we've covered, okay? That will take you even less time because it's a really easy test, but it covers all the chapters that we've had. It will be matching, unlike these have been multiple choice, so it'll be matching. So it's pretty easy. Now, sorry about that. I don't mean to make it too easy for you. Okay, then, oh, and by the way, since those together won't take you an hour, that's why we're going to have pizza at 12. Okay, and I'll provide the pizza, whatever y'all want to drink, as long as it's non-alcoholic, James, it'll be fine. Y'all bring whatever drinks you would like to partake. Okay? Say that one more time. No. This is the only one so far. The thing is it meets right at noon, is one reason. And the other thing is a small class, and it doesn't take long to take the final, so I figured why not make it worthwhile. Now, I haven't seen or heard anything about student evaluations, course evaluation, student course evaluation. Are they out there? Okay, fantastic. I was going to ask that today if you had seen anything, so please do those. Otherwise, you get no pizza. No, I'm just kidding. I would do that to you. But please do. We do value the student course evaluation.
I was in class one time, the teacher would let us take the final.
I know. I think that's blackmail. I mean, I think that's unfair. So, I mean, you're adults. If you don't want to do it, for me to force you to do it, probably I would not get a good reflection of what you really think of the course. You'd probably be so angry at me for making you do it, it would come out biased.
Let me tell you what you need to do, though.
What's that?
You need to have us do it for extra points.
Okay,
Just
then
15 or
people
20.
will tend to overinflate. So I'd rather you be honest about it. Just please do it. Please do the student course evaluations. We do value them. I usually try to give points for physical science, not for course evaluations. Okay, so, all right. Any other questions? And by the way, I do want all of your work in, so any labs or tests that you haven't completed and turned in yet, I need them in by Thursday because I want to return everything back. I've returned most of everything back to you. As at the very first class, I was going through the things I was missing, and there's not very many, but a few of you, there's a couple things I don't have yet, so please get those in. All right, any other questions? All right, this chapter 23 is weather and climate. However, we're going to do, no, actually we will do it in that order. It's rocks and minerals we do in the other order. This one we do in that order. The core concept here, which you find on the leading page of your book, 573, solar radiation, actually, they changed it a little bit. Your book says solar energy drives cycles in the Earth's atmosphere, and some of these cycles determine weather and climate. Okay? So whereas here it says radiation, your text says energy, solar energy. Both of them are true. I mean, the solar radiation is solar energy. I guess they just picked a smaller word. I don't know. And sure enough, that is true. Unfortunately, we had to skip the atmosphere chapter. That was chapter 22. So anything that, if they're talking about it in there and you don't understand it, go back and look at 22. You may fill in the gaps. I will try to fill in any that may be missing that I see, but you may recognize some things that I wouldn't. I'll just assume everybody would know. Neat little picture here. This shows, anyone want to make a guess? Yeah, it sure looks like the Gulf of Mexico to me. This would be the coast of Canada, probably Canada, Texas, and probably Mexico here. This is pretty much the Florida Peninsula. I think that's Cuba right down there. You can't see it all because the clouds are covering more of the landmass, and the different clouds are covering the sea. Or, well, actually the clouds are more transparent. You see the sea here in the looking at landmass, it's harder to pick it out. But sure enough, that looks like the Gulf of Mexico to me. Okay? And it shows, basically, you can see something's happening with these clouds. They're formed sort of striations here. You know, what's going on with that? Well, we'll talk about some of the stuff that could be attributed to those effects. Now, your picture in your book, the new edition, shows a pretty beach scene. Where it looks like a big thunderstorm about to hit, which we haven't had our one today. It's probably still going to come. So, wait, it'll be while you're taking the test, won't it? Okay, good. Okay, so we'll hold off until the test for that. So let's start with clouds and precipitation. Okay? Now, if you haven't failed to note this yet, please start noting it. Lots of things in here goes in cycles. We had rock cycles. We had the principle of uniformity. Everything that basically is happening has happened before, and what's happening now will happen in the future. Here's another, the hydrologic cycle. Now, what do we mean by hydrologic? Okay, almost. What else? Hydrogen, but with an O. Water. Hydrogen oxide, which is water. Hydrologic cycle. Okay, what's first, the chicken or the egg? Who knows? But let's just start with the ocean. That would be the next chapter if we get there next time or not. Start in the ocean, the sun, and guess what? 70% of their surface is covered with water. So lots of that solar radiation, solar energy is hitting the ocean, And as it hits the ocean, it's evaporating water from the ocean that makes its way up into the atmosphere. Somewhere up there, it gets cooler, and they start condensing into little droplets called clouds. The clouds, the prevailing winds, mostly in the temperate region, they're westerly winds, blow off the Pacific Ocean, carrying these clouds over the continental U.S., North America, South America. Okay, so the clouds go over land. When they go over land, then they could hit things like mountains that are very cold. Now the temperature drops and the clouds can't hold that much moisture, and here comes the rain. The rain falls, hits the ground. We studied in the last chapter that some of the water, of course, hitting the ground goes into the ground, but much of it runs off. It continues running off until it goes back into the ocean. Okay? So there are diversions in between. For instance, some of these clouds, they have storms over the ocean. They fall right back into the ocean and so they short circuit the cycle there. Others, the clouds make it over land, and some of the moisture does go into the soil, into the groundwater, and may stay there for long periods of time before they ever get back to the ocean. So they're not always short cycles. Sometimes they're long cycles, sometimes medium cycles, and sometimes it goes around pretty quickly. Okay? But basically, everything goes through that cycle eventually. Okay? The number 2 is here, transported through the atmosphere. Sometimes it gets over land, sometimes not. Ultimately, at some point, the clouds will condense. Those droplets in the clouds will condense with each other, forming bigger and bigger droplets until they become drops, and when they get heavy enough, they fall to the earth. The falling is what we call precipitation. Okay? Dew in the morning is not precipitation. Frost in the morning is not precipitation. Something falling out of the sky, rain, snow, sleet, that's precipitation. Hail, that's precipitation. It's only the stuff falling out of the sky, not the moisture that was near the land anyway, it cooled overnight and condensed. Okay? So that's condensation and precipitation, and ultimately returning to the ocean. And like they say, there's many smaller cycles. It could be, have any of you ever lived up near the Great Lakes? Okay? The Great Lakes, they're big enough bodies of water. They produce enough moisture sometimes to produce lake effect snow and lake effect rain. Not coming from the oceans, it's coming from lakes. So you may have a short cycle here, you may have a short cycle here, you may have a longer cycle where this soaks into the land and goes into the groundwater. You know, all those things can be happening. We're going to focus on the weather and climate part of it. Okay. And by the way, what's the difference in weather and climate anyway? Are they just two synonymous words that just sound good together? Or is there a difference? Say again? There is a difference. Is that what I heard? Or, okay. I agree. Okay. What is that difference? Or what could be? Would be.
I guess weather is just a temporary thing.
Yeah, weather's what's happening today or recently or something. Whereas climate is the long haul. What has been happening over time. Yeah, very good. Okay? And weather changes day by day, hour by hour, you know, week by week, season by season, certainly. Climate also changes, but they're much longer cycles of climate cycles. Okay? So let's start with where we began here, forming those clouds. Evaporation from the ocean going up and forming the clouds. The cloud forming process. The clouds form when the air masses, and we're going to talk about those later, the air masses are cooled to their dew point. What in the world do we mean by dew point? Okay, question. Do we have any water in the air in here?
Yes.
Yes, definitely. I would say the humidity in here is probably 40 to 60%. That's just a guess, okay? Yeah, there's plenty of moisture in the air here, but do you see any of it? Do you feel any of it? No, it's all evaporated into the air. Now, if someone had brought in a nice cold glass, not styrofoam, nice cold glass of iced tea or ice water or something else, do you have some over there? I bet you do. Even styrofoam. Some of that moisture from the air condensed on this cup because he has ice in there, right? It's cold. The cup is cold. So some of that, near that cup, the air reached its dew point. In other words, the point at which it couldn't hold the moisture anymore. Okay? Now, that's part of the thing that makes summer in the South sort of miserable, okay? Because we do have high temperatures. Shoot, in Arizona, they've had 120 degree days already. Now that's hot, and that's miserably hot. But you know what the people from Arizona say when they come here? Take me home, because the humidity gets them here. What difference does that make? Our temperatures are probably 20, 30 degrees cooler than out there, but our air, because we have Gulf of Mexico, thank you very much, down there, it just pumps the humidity in here, and the air, and now their air at 120 degrees could hold tons of water, but it doesn't because there's no water out there. So that's what they call dry heat. And you don't suffer as much unless you dehydrate too much, because anything you would sweat, and in 120 degrees you will sweat, but it immediately evaporates, And you feel a little cooler because that evaporation of water, you're losing 540 calories of heat every gram of that water. And a gram is a small amount. Every gram of water that evaporates off of you, you're losing 540 calories of heat. Whereas Sunday afternoon, shouldn't be working on Sunday, but we were doing a little bit. Went out. My wife we had gotten some coleus, really pretty coleus from garden shop early in the spring, and we had planted them in a couple of our planters, and those things, with all the rain we've had, they've just been growing like crazy. So my wife, in some places, the green ones are covering the purple ones, so she's pinched off some places, or cut them, I don't know how she did it, where they were just getting too growthy. And rather than throw them away, she stuck them in a thing of water. And they rooted, okay? They're really succulent type plants, so they'll do that nicely. And so she had done a bunch of those several weeks ago, and they all had pretty good root systems on them. And she said, well, let's plant them somewhere. So we went out and found some places and some other pots and various things. So I was planting that. And I mean, that was 30 or 45 minutes out in the shade doing that. I was soaking wet. Why? Well, I was sweating, yeah, but number two, the reason the sweat wasn't evaporating, it was probably 80% humidity out there, meaning the air couldn't hold much more moisture. It was already pretty close to its dew point, so therefore my sweating, which is the body's way of air conditioning itself. I mean, it's air conditioning. What's the air conditioning system doing wherever it happens to be? The first thing it does is compress a gas, Freon, something like that. They don't use Freon anymore, but compress it, and then let it expand quickly, and that's what does the cooling. Okay? The compressor blows the heat off, brings it in, and then the condenser lets it expand quickly, and then it drops the temperature. Well, the reverse of that is happening here. The body is producing sweat, so it will evaporate and take the heat away. When the air has so much moisture in it, 80, 90% humidity, it won't accept anymore. So you just stay hot. So actually, you can almost more likely have heat stroke here in the southeast at 90 degrees than you would maybe in Arizona at 120 degrees. Because there, your body is evaporating. I mean, you don't even feel the sweat. It comes to the surface, evaporates immediately because the air is that dry. Because it's way below its dew point. So the dew point is the point at which and this is in the previous chapter, that's why I'm going over it so much, the temperature at which the water comes out. And if you have a 90% humidity, you can't drop a few more degrees before you're going to be 100%, then you start having precipitation. Okay? Where out there, 15% humidity, it could drop 15 degrees and you might only go up to 20% humidity because they have a long way to go. So that's what they mean, the dew point. So these clouds are when the air masses, and we'll talk about those later, are cooled to their dew point. And when they are, then the little droplets start forming. Like I said, when it's evaporating off the ocean, you don't see it like you don't see the moisture in this room. But when it gets way up in the atmosphere where it's quite a bit colder, then they start falling out as little droplets. Generally, they're cooled by the upward movement, and that's called convection. We've talked about that before, haven't we? Convection is warm air rising and cool air coming down underneath. So that warm, moist air is carried up until it hits an area out there that's cool, and then it cools and comes back down. It's also cooled by barriers. And this is what I was talking about before. Those clouds off the ocean come sweeping across the ocean until they reach, say, the west coast of the U.S. And remember, the west coast of the U.S. goes straight up. East coast, you have a long, gradual continental shelf, and you have the coastal plains, and finally you get to the foothills about 50 or 100 miles inland, you finally get to the hill. On the west coast, you come off the ocean and almost go straight up. Okay? There are beautiful vistas that you have out in California. People build right on the ocean, but they're hundreds of feet up, because the hills go straight up. Okay, so they hit these barriers. They could be mountain ranges. Think about it. What's one of the wettest cities in the U.S.? Seattle, Washington, exactly. Go into eastern Washington and you're in a very dry climate. Why? Because you have the Cascade Mountains in between western Washington and eastern Washington. They hit those cold mountains, all the rain falls out on Seattle, on Portland, and all down there, hardly any moisture makes it across the mountain range into eastern Washington. That's a pretty dry area over there. Okay? So you hit these barriers. So they're cooled by convection, going up into a cool region. Barriers are colliding air masses with different densities. For instance, can't say it's going to happen now, but one of the rain events we had earlier, and you go back into the spring, and this is very common. This time of year, it's just so much moisture in the air that every now and then suddenly it reaches it falls, But especially in the winter and the fall and spring, to some extent, you'll be nice and warm, even a little muggy here, and then here comes the cold front. When that cold front gets here comes the rain. And then the cold front pushes the rain out, we say. Basically, it calls the rain, come in, and then it's colder, drier air behind it. So colliding with air masses with different densities, okay? That will also cool that. So it's cooled by three things. I would put upward movement here with convection, barriers, and colliding with air masses with different densities. The upward movement is more there than it does with these two. The cloud formation depends on the atmospheric stability. And you'll hear James Spann, Jerry Tracy, and all those weathermen say, oh, we got very unstable air today, or we really unstable air today. You don't have to worry about rain. What are they talking about? Stable or unstable air? What do they mean? Maybe the next slide will say, atmospheric stability. A stable atmosphere will be, now remember, we talked about air being lifted by convection. Okay, let's just imagine that it's not just air, but it's a little packet of air. Okay, we're going to take this little bucket of air here and watch it as it rises. Okay? So this lifted parcel of air, as it goes up, if the lifted parcel of air is already cooler and denser than the surrounding air, no sweat. That's a pretty stable situation. The lifted parcel returns to its original level and is happy right there. Very stable situation. The unstable situation is when the lifted parcel of air is warmer and less dense than the surrounding air, so it wants to keep going up. Okay? Well, it's moved to a higher level, it will continue to rise and cool, and when that happens, especially if it does it fairly quickly, it starts sucking other air up around it, and then you could have a thunderstorm. Now, I've heard Jerry Tracy, that's where he usually goes, talk about this, the difference between stable and unstable air. He said, if you can imagine, and Jerry is not a big man, he's about average size and stuff. He said, y'all know who Arnold Schwarzenegger is, right? Used to be Mr. Universe and Conan the Barbarian and all those other things. And Governor of California, by the way, but very strong. He probably can't do this today because he's getting a little older, but it wouldn't have been in his prime much of a problem for him to pick up Jerry Tracy and hold him in the air. Maybe not forever, but for a bit of time. I mean, he was really strong. That would be fairly stable. Okay? But if Jerry Tracy would try to lift Arnold Schwarzenegger up and hold him in the air, that would be very unstable. He would be dropping him and falling down himself. And that's how he does it. If this lifted parcel of air is cooler than the surrounding air, it goes up and it's not going to do anything. It goes to its original level where it's happy and stays there. But if the lifted parcel of air is warmer and less dense than the surrounding air, then it goes up, keeps moving up, and causes these thermal currents to move up. Okay? They show these graphs, which are okay. Okay? I just don't think they're as instructive as they think they are. Here we have temperature on the horizontal scale, increasing as you go to the right, and increasing altitude here. You're going up higher and higher in the atmosphere. Okay? Now, if your situation is the temperature at ground level is here, and as you go up, the temperature is just falling off slowly. And this parcel of air, the temperature of the rising parcel of air, actually is less than the surrounding air. If it's over here in this, and it's not got as much moisture in it, it can rise and nothing's going to happen. I mean, it's just perfectly fine. The temperature of the rising parcel of air is over here. It's well below this. It's, everything's hunky-dory here. Okay? But that's the stable situation. The unstable situation is if the temperature of the surrounding air starts at the same level, the temperature here on the Earth, on ground level, but then drops off real rapidly as you go up, and then that same parcel of air, same temperature and everything goes up, but its temperature is higher than this. So immediately it gets into cooler air, and this is an unstable situation. It's just going to keep trying to rise and rise. If you'll notice, the arrow there is up, the arrow here tends to be down. It's going to rise until it gets comfortable, and then it's going to just hang there. This wants to keep rising, okay? And keep rising and drawing more air up around it, and then at some point it's going to lose the moisture it holds and everything else. And that's going to be your stable situation. Now, the big deal here is what's happening in the atmosphere. That here you're at one temperature and very quickly it falls off. The stable situation was, here was at same temperature at ground level, but very little change going up and very gradual change. So this, notice, was the same on both of them. Okay? So it all depends on what that the surrounding air is doing. If you have a rapid drop-off, there's a real good chance you're going to have some storms. That's what you call the unstable situation. And those are the thermals rising quickly and cooling fairly quickly. Because you see the temperature drops off real quickly as you go up. Okay. So let's look at this upward mobility with the moist air. The rising moist air cools, eventually reaches the dew point. That's the key here. At the dew point, then the air can't hold that much moisture anymore. It's cooling, it was warmer, it can hold. Now, think of this. When something heats up, the molecules move faster. Okay? Agreed? That's why warm air rises. It becomes less dense. Okay? That's why any of you live in two-story houses or apartments or anything like that, the upper floors is always warmer than the lower floors because the hot air rises. Okay? And they call it also the chimney effect. That's why chimneys, they use chimneys because the heat, smoke rises. Okay? Hopefully it does anyway. It doesn't go into your house. Okay? So this rising air, as the temperature gets less, the rising air, which has a fair amount of moisture in it, but it's fine, like the air in this room, but as it goes up, it reaches the dew point. The air can't hold the moisture any longer. The droplets condense around these things called condensation nuclei. Okay? The air gets very close to saturated, close to 100% humidity, and the air, moisture in there saying, I can't hang around, anymore. It can't hold me any longer. Oh, I was going to talk about this. When anything warms up, the molecules move faster. Okay, that's what temperature is, the average kinetic energy of the molecules. Okay, so if the molecules are moving faster, they're bumping into each other harder and spreading each other further apart. The further apart they are, then the more moisture they can hold in between. When they start cooling and coming down, they say, hey, water, get out of the way, That's not quite what they say, but something like that. And the droplets start looking for something to condense around. Those are called condensation nuclei. If you have no condensation nuclei up there, which most of the time you have some, you can actually get supersaturated air. And that leads to some strange situations. So, what are some of those condensation nuclei? Well, over the ocean, most of the time it's just the water that goes up. But if it's evaporating quite quickly, some of the salt crystals that would have been left actually get carried up high in the sky too. They become great things for water to do it. Sometimes it's dust particles, okay? They actually say that most snowflakes start around a dust particle. And that's why my mom, being a nurse, said, don't you eat that snow. It's got dust in it, She was always worried about it. So, that must be good to eat. Yep. Okay, so the cooling of the rising air is slowed by the release of the latent heat of vaporization. What in the world do we mean by that? Anyone know? Latent heat of vaporization. See, let's move. Are you trying to say something?
I mean, it takes like the sun to evaporate, right?
Right. Okay. And that's really good thoughts right there. Okay. If you think about it, when you go to the beach, as you're driving south in the summertime, we don't do this much anymore because of this miserable traffic going there. It just gets worse and worse. If you're driving south, usually the temperature is rising, right? You get down to Montgomery, goodness gracious, it's hot down here. You keep on going down around Evergreen. My word, it's hot down here. You go in, keep on going south. It just seems to get warmer and warmer. But then when you get right on the beach, it feels cooler. Part of the reason for that is that the heat from the sun is evaporating water, which drops the temperature. Okay? That's called the latent heat of vaporization. If you were to boil a pot of water and you had a thermometer in there, okay, you would see, if you turn it on the stove, you'll see that temperature go up and go up and doesn't go up. Now, what kind of thermometer you got? Centigrade or Fahrenheit? You tell me. Fahrenheit, okay. So the temperature may start around 70 degrees. If it's tap water just out of the sink, maybe even less than that, depending on, okay? And you put it on, you turn on the heat, and you see the temperature start going up, going up. And when finally it reaches or gets really close to 212 degrees, which is the boiling point of water, when it gets up to there, then the water starts boiling. You can turn up the heat if you wanted to then. The water will boil faster, but what does your temperature of the water do? It doesn't go up. It stays at 212 degrees Fahrenheit. As long as there's water present, it's at 212 degrees Fahrenheit. Okay? As soon as, yeah.
Same thing with a liquor seal.
Okay.
You know, it's legal to do that here, you know, for personal use. But it's 176 is the boiling point.
The say again?
176 is the point for alcohol in the boil.
Yeah, okay.
And it'll stay there until all
Right.
the alcohol is gone. Then
Yeah,
it'll start
exactly.
going up.
Exactly. Okay. He's been making that. Okay. White lightning. Okay, never mind. Okay. So, what is happening then? You're adding more heat to the water, but you're not changing the temperature. What you're doing is changing the phase from liquid to gas. And that takes energy for that to happen. But you don't see a change of temperature. You don't feel a change of temperature. That's called latent, meaning hidden. The hidden heat of vaporization. Okay? Same thing happens when you're cooling something. You've got ice and what? Water or something else in there?
Ice.
And
It
it was tea. Okay. Let's just say it was ice water to begin with. Or let's just say it was water. So you started out at 70 degrees, you know, right out of the tap, and you put the ice in there. Well, of course, the ice starts melting until you get down to 32 degrees Fahrenheit. 32 degrees Fahrenheit, that's the melting point and the freezing point, melting point of ice, freezing point of water. Okay? And as long as you have ice and water in there, your temperature is going to stop and stay at 32 degrees. You may melt more ice, but all it's doing is equilibrating in the atmosphere, in the room temperature. You know, it's gaining heat from the room. Okay, that's the heat, latent heat of condensation or freezing. Okay, so there's two latent heats. Well, when the rising air does start coming out and the water droplets forming, then that heat is released, so the cooling slows down. Okay, because now the water, as it condenses, is giving off heat, and that heat keeps the rising air from cooling as fast. Now, a huge number of droplets appear in the clouds. It's a pretty cloudy day out today, and you would not believe how many tiny little droplets of water are in there, but that's what a cloud is. When the sun is shining on it like it is looking out there, they look bright white because you're reflecting the sunlight off the cloud. But if you're underneath it, they're blocking the sun from coming through. They look black and dangerous, okay? And they can turn into rain, which will happen when we start taking our tests, okay? So that's how the cloud forming process begins. Okay, now they have a little blurb in a little example here. I think they had a blurb that I skipped over. Science sketch. I won't mess with that. Example 23.1, a parcel of air with a volume of 1 cubic. Wow. 1 cubic kilometer. That's some parcel of air, okay? That's 1 kilometer. That's a sixth of a mile on each side, length, width, and height. Boy, this is reasonable, isn't it? Contains 1.65 times 10 to the third kilograms of water vapor, rises to an altitude where all the water in the parcel condenses. What is the change in temperature? Well, that assumes that you know about specific heat, that you've done the things in the first half of the book. We haven't, so we won't mess with that anymore. So let's go Origins of precipitation. Boy, that's a pretty thunderstorm looking picture there on the right in 577, isn't it? So, precipitation is water returning to the Earth's surface from the clouds. Dew and frost are surface processes, not precipitation. What dew and frost is, and they're basically the same type of thing, it's just dew in the summertime, frost in the wintertime. It's when the air and the heating of the day picked up and carried a fair amount of moisture in it. Then at nighttime the temperature drops. And now the air right above the ground can't hold that much moisture anymore, and it comes out as dew. Okay? In the wintertime when it can't hold that, but it's already close to or below freezing, then it comes out as frost. So those are surface processes, not precipitation. Precipitation is when the clouds way up there reach their condensation point and start dropping it out. That's precipitation. Precipitation forms in two ways. Now, here's the first of these. Coalescence of the cloud droplets. Okay? Now, this is happening mostly around the equator. Okay? Around the equator, you have a lot of energy there, a lot of heat from the sun. It evaporates the water rises, and in very short order, it can't hold it any longer, and it falls out. That's coalescence of the cloud droplets. And that could happen here too. But actually what happens more frequently, especially in the really bad thunderstorms, those clouds go way up into the atmosphere. And when you look out across and see one of those big, tall, booming clouds with sort of an anvil shape at the top, those are called the cumulus clouds. They are so far up there. What's happening there, this warm, moist air that's sucked up, goes up that process we were talking about, unstable process going up there, get into the way high atmosphere. The water droplets start coming out. They reaching close to the dew point, but they keep rising till it gets getting colder, and now they form ice crystals. Okay? Those ice crystals, they keep growing. Okay? Because more moisture is coming up, more moisture is coming up. And those ice crystals finally get so big that they start falling. Now, in the summertime here, they fall from a pretty far distance. By the time they reach the ground, they've all melted. But when I remember traveling with my family in the summer. That's the only time we go anywhere. And you just drive up and suddenly hit this storm that came out of nowhere. Those droplets, as they hit the window, whack, I mean, it's almost scary. Big old drops of water. You can almost guarantee those were ice crystals. Get that big, and that just didn't come from coalescence of cloud droplets. Those were ice crystals that grew and grew and grew and finally fell, and as they fell, they melted and hit your windshield. So let's talk about the coalescence process. It takes place in warm cumulus clouds near the tropic ocean. What are the tropics, basically? Remember that from my earlier chapter? The tropics. Cancer and Capricorn, where are they? Say again?
Near the equator.
Yeah, they're near the equator. How near the equator?
23 and
a half degrees, exactly. 23.5 degrees north, 23.5 degrees south. I'm pretty sure Cancer's on top, Capricorn's on the bottom. Thank God. Always get those crossed up. Okay? So, those are your tropical oceans. Okay? Down near the equator. Okay? The clouds contain giant salt crystals. Those are your condensation nuclei there. That evaporation is going on so rapidly there, they actually pull up some salt crystals. They didn't mean to, but they carry them with them. They form your condensation nuclei. Okay? They're salt crystals. The ice crystal process takes place in clouds in the middle latitude. Guess what? That's where we live. Okay? Now we're in the southern part of the middle latitudes, but we're still in the middle latitudes, and those big booming thunderstorms. Now, let me give you an example. When I was, my very first permanent duty station in the Navy was an ammunition ship. And when I went to join the ship, it was just coming back from a Westpac deployment, Western Pacific deployment, off the coast of Vietnam. That was back during that time frame. The war was pretty much over with, but they were just coming back from the area, and they were on their way home, but they flew me out to catch the ship. And because they were afraid it would leave Subic Bay, Philippines before I got there, they flew me to Guam, which was the next place it was going to. The trouble is, I got there 5 days before the ship did. So they put me up in the BOQ in the middle of the island with no transportation. Okay, and not a lot of money either. I just had gotten in, just graduated from college, so I didn't have, I didn't had my first paycheck yet. So I was kind of, not wanting to spend a lot of money, waste a lot of money. I didn't have any. So it was really boring, and I read and I did as much as I could. It's a pretty island, So I would, and it's near the tropics, okay, Guam. And so I got to thinking, well, I need the exercise anyway. But I didn't have any transportation, couldn't get to the beach or anything. So I thought, I'll just walk, see what the island's like. So I would take off and just go on a walk. And generally when I got about an hour to 2 hours away from the BOQ, about the time I thought, yeah, it's about time to turn around and go back, I get ready to go. And I mean, there was no warning. It just, that was this stuff, coalescence process. The day was moving along. The air was hot, evaporated water. It's an island surrounded by water. Took all the water it could take, and then just fell out. Not a big storm, not a big air mass or anything else. But around here, most of the time, you can almost tell when there's a storm coming. I mean, there's some days it'll happen like that, but the big storms, you'll see them rolling in and stuff like this. And this will be because this is what we're talking about. Ice crystals capture nearby water molecules and then freeze that. And they keep freezing and bigger. And finally they get so big, grow so heavy, they can't keep going up, so they start falling. They leave as ice as they're coming down. If the air is warm around them, like in the summertime, they've all melted and turned to rain by the time they reach the surface. But if you're far enough north and the air temperature is cold enough, they come down to snow. And you know that some snows, it almost falls in clumps. That's the big group that, they didn't get down. Other times it'll just be little flaky stuff, Still pretty here, we like to see it, but we don't want to live in it too long, okay? All right, so that's the origin of precipitation. Now, what produces that precipitation? And this is 23.2, the weather producers. Now, this is an idealized model. It doesn't ever work just like this, but you get the general idea. In the region between 10 degrees north and 10 degrees south, in other words, really, really, really close to the equator, you receive more direct solar energy than anywhere else, on average, right? So that region is getting more of that heat. The air heats up. It rises, okay? Let me get my globe in here. And I just find it kind of interesting. I don't think there's anything really to this. I'm too far from a microphone. But I'm going to sit here while y'all are here. If you look at this, the equator goes through a fair amount of South America, but there's lots bigger pieces. Look how much ocean it goes through. There's a little bit of Borneo, but not too much. A little bit of Indonesia. Even Africa. Look how thick Africa is here, but it only goes through there. So most of the equator is over water. Big chunks over water. We're talking about 10 degrees north and 10 degrees south of the equator, so that would be just this region here. Okay? Not even halfway to the tropics. That's 23 and a half, as James said. Just 10 degrees north and south. So the direct solar radiation hits there, evaporates the water, the air heats up and rises, spreads toward the poles. Okay? What does that leave? Okay? The air cools as it goes up, becomes more dense as it rises, sinks back to the surface at latitudes of near 30 degrees north and 30 degrees south. Where do we live? 33 degrees, 23 minutes, 45 seconds. Well, we don't all live there, but that's here, about where we are here. So we're at the place where the air comes back down. It leaves the poles, rising, going up, it cools, and then comes back down around 30. Okay? 30 north and 30 south. What's the end result? You have near the equator a band of low pressure, because that's where the air is rising from, and then bands of higher pressure around 30 degrees north and 30 degrees south. Now, there's one of the labs that I do in my physics classes, and in the physical science 112 class, that we need to determine temperature. Okay? When we determine temperature, we also determine pressure. Well, actually, we don't really need the temperature that much, it's just the pressure. And to begin with, before I taught this chapter, this book any, every time I do that lab, I would expect, since we are far from sea level, not real far, but we're, 200 miles north of the Gulf of Mexico, is that about right? 400 miles north of the Gulf of Mexico. And you're rising most of the way, so you're above sea level. I would have thought we'd be a little bit less than 1 atmosphere of pressure, because that's usually what you are up near the ocean. Okay? And every time we did that experiment, I'd say, y'all look it up and see, they had the phones, look it up and see what our atmospheric pressure here is in Birmingham, Professor. And they look it up, and it would almost be right at normal atmosphere. Why aren't we below? Why is every day we're in a high pressure? That's why. Because we're at the place where that air comes back down. Near the equator, even right on the water, you'll be less than that most of the time. What's the end result? The low pressure near the equator, high pressure near 30 north and 30 south. You have these large convective cells try to form to equalize those pressures. Okay? So in other words, you have cells of water from the equator, trying to equalize pressure there, and you give off pressure here, so these things are happening. That's what starts the process, or is part of the process of producing weather, this inequality of pressure. And that leads to these air masses. And we've already talked about air masses a couple times. They've been mentioned. What do we mean by these? These are large, basically horizontally uniform bodies of air that sit over the top of the Earth. They contain certain amounts of moisture and certain temperatures. Moisture and temperature conditions are nearly the same in this huge mass of air. Okay? 4 main types. Those that are over the continents, like North America, where we live, South America, Africa, Asia, Europe, Asia, okay, Australia, over the land masses, these are called the continental land mass, or air masses. 2 types of those. Up in Russia, polar, okay? You're awfully close to the pole. Antarctica, polar, okay? The very southern part of South America, polar, okay? Northern Canada, Alaska, polar. Those would be polar, continental polar air masses. And then you have the maritime polar. That means it's over sea. This is over continents, this is over sea. In French, mer, M-E-R, is the sea. So this would be maritime polar. What would be those? That over the North Atlantic, the Bering Sea, the all the water around Antarctica, water around South America. That is all maritime polar. Then we have continental tropical. That would be anything here in northern South America, anything here in much of Central Africa. India would be a little bit of that. Certainly Indonesia would be. The northern part of Australia would be that. But that would be more tropical, the continental tropical. Maritime tropical, that's all the rest. I mean, that's all this ocean that's right near the equator. These are our four main types of these air masses. Now notice what it is. Are they overland or oversea? And are they warm or are they cold? Cold or are they warm? Okay? These dictate what we call the air mass weather. Okay? The air mass weather, or when you have big systems moving through. The weather conditions remain the same over several days. Sometimes that's good and sometimes it's not so good. I can remember many summers, I grew up on a farm in Georgia, when we just suffered through day after day after day, and they called it a Bermuda high. Now, why they called it Bermuda high, I'm not really sure, but here is Bermuda way over here. Thought it was. Yeah, there it is, Bermuda Island. Okay, all I can see was Hamilton. And as long as that had a big high pressure ridge around it, and high pressure flow is clockwise, that high pressure flow, and we lived in Georgia, it kept hot, sometimes humid air, but never enough for rain. And it would just sit there for weeks on end. And we would suffer. The plants would suffer. It was miserable. Okay? Weather conditions would remain the same over several days. Weather changes when a new mass moves in or when the air mass acquires the local conditions. Okay? Now, I can't say what's been happening this summer. It is such a rare summer. I mean, what's that?
I said it is such a rare thing.
I know. I mean, I can never remember having this much rain this far into the. I mean, this is the hottest part of summer. I mean, it's hot and humid out there, but we haven't had a 100-degree day yet. We haven't had an upper 90-degree day yet. We've made some days into the lower 90s. I don't think we've cracked 95, have we? But it's been hot because of all that humidity. But just like every time it starts to get real hot, there will come more rain. You know, and that takes away some of that heat. So, I can't say what's happening this year, but it's actually been fairly nice. Usually by this time of year, my wife uses the phrase, boy, don't the trees look tired? Don't they look sad? Because the leaves are sort of droopy and you start getting them falling off. Right now they're all just the green, like, wow, we got plenty of water this year. Okay. So here we have a picture of the U.S. And of course, what are we going to be fed by here? Because you got the South Atlantic, or not South Atlantic, the sort of equatorial Atlantic that feeds in here. Gulf of Mexico, a nice hot bathtub here. That's feeding in, this is maritime tropical. Okay? Up here in northern New England, you have air masses coming down from off the coast of Canada, but off the coast, and these are maritime polar. Here, and quite often, if you notice in the wintertime, they used to do this more. I remember the weather stations will also always quite often say, and the coldest spot in the nation tonight was, or last night was, it was almost always somewhere like Great Falls, Minnesota, or somewhere in Wyoming, but somewhere here. These were continental polar. coming off of Canada. In fact, I remember a couple of times we've had what they call the Arctic vortex. Remember those? Man, they brought some cold weather. And that was continental polar air masses. Over here in northwestern U.S., you get maritime, but sort of some of that is polar. The temperatures out here tend to be a bit cooler. Down here is maritime tropical again, okay? But then off Mexico is continental tropical, and there you made your way all the way around. Those are the big air masses, okay? They dictate air mass weather. Now, if one of these hangs around too long, then they pick up the local conditions. You no longer have a distinctly different air mass, okay? So that's what they mean when they requires a local condition. They either warm up or cool down, whatever, to get what you had to begin with. So what are weather fronts? You always hear the weathermen talking about this. Well, we got a cold front coming in, or we got a warm front coming in, or we got a stationary front. What in the world do we mean by that? These are the boundaries between those air masses that are at different temperatures. Now, we sure don't seem to get them much, or we don't notice them much. Cold fronts coming down from Canada at this time of year, they just don't seem like they happen, okay? It may be they're coming across the U.S., but warming up as they come. By the time they get to us, you don't notice that's a cold front, hardly changes a degree, But that's what it is. A cold mass moves into and displaces the warmer air upward. Well, if you think about cold air is denser, so when the cold front comes in, it kind of plows, I like to use that term, the warm air, it makes it go up. Guess what that is? Unstable condition. That's just about like the picture we had earlier. Quite often when the cold fronts come in, moving the warm air upward, then you get that unstable situation. The moisturizing air is cooled, leading to large cumulus and thunder clouds. There comes the rain. Okay? Now, on the other hand, what if you've had that cold air sitting on you? I can't imagine that at this time of year. And then here comes a front from the Gulf of Mexico. And we have this happening a lot. That warm air advances and rises over the cooler air mass. Now, then, sometimes you have a longer, more gently sloping front, and quite often then you just get clouds and some rain, but not as harsh a rainfall. Let's take a look at the figures for those. Oh, this one doesn't say a lot. I mean, I know what it's saying, but it's not a particularly great figure, I don't think, for what they're doing. All right. And you hear the weathermen talk about this. Talk about high pressure coming in off the coast of Central California. High pressure in the desert, southwest. High pressure over Texas. High pressure coming down from Canada. Those are your high pressure. I only see one low on here. Oh, there's another high pressure over Montana, North Dakota, somewhere around there. But here's a low pressure area. Now, of those, which seems to be the most serious? Any ideas? The biggest weather maker here is that low pressure. And here's why. Look at this high. It doesn't even show a complete circle around it, and it's really dispersed. This would be like you just did in your topographic maps, where you don't have those lines close together, everything's about the same. Those are level areas. When it's rising sharply, like hills or mountains or ravines and stuff, there you have them very close together. Well, here the high pressure is really spread out. Here you have a sort of a circle here, but where's the next closest? Here you have maybe one circle, another one not too far away, but they're really spread out. Okay, here hardly anything happening here. Here, one circle. But look at that low pressure. You have a small circle here, another one there, another one there, another one there, and especially right in here, what that is saying to you, you have a big gradient of pressure. It's changing a lot of pressure over a very short space. That means you're going to have very strong winds right there. Very strong winds. Usually low pressure also means you're bringing in moisture, and the air rotation around low pressure is counterclockwise, so it's bringing that in. Depending on what time of year this is, that could be a severe snowstorm happening up there. They call them the nor'easters, or in the summertime, a heavy, really fairly violent thunderstorm type area. Okay? So the fronts are, the weather fronts are the boundaries between the air masses at different temperatures. And here you see a front here, and they don't really define it too well, but this looks like a tropical polar air mass forcing its way south. Now, if this is wintertime, that's a bad news coming, okay? Because that's moving its way south. Over here, I can't tell what's going on. I'm guessing the one before that is trying to slowly push its way out here, and maybe this one's pushing its way in, but this is interfering with that. And if this is counterclockwise wind, some of this is coming down in cold air, both maritime polar and continental polar is coming and pushing. So this almost certainly is a cold front pushing along here. This is probably, could be classified as, I guess, a cold front too. But this looks like what they call a stationary front. It must be hanging in as a cold front. So I'm guessing these are cold fronts. Now that's a lot of guessing. I wish Jerry Tracer were here. He would tell us exactly what that meant. Okay, with the cold front, okay, let's look at a better illustration. Here is the cold air mass coming in. This would be a cold front. It's coming in, and it's a lot like a snowplow. It's pushing that warm moisture air that was above it up, out of the way, and that's what gives you instability. When that happens, you usually get pretty severe rainfall right there. This is the side view. The top view is looking down like this, and you see that front coming up on the city here and pushing the warm air up. Whereas, oh, don't tell me it's not going to show it. Yeah, you'll have to look in your book, okay? And by the way, your book has, let me go back a slide, I wasn't keeping up. This, whereas this picture is just those little bitty bubbles of clouds around pushing down, the one in your book shows a much better shot, okay? Huge, it shows not just the U.S., but all of North America pretty much. Shows the continental polar coming in from the polar regions across northern Canada, maritime polar coming in from the cool waters in northern Pacific, maritime polar on the east side was coming from the cold waters over the northern Atlantic, the continental tropical coming out of Mexico, pushing up, maritime polar, maritime tropical coming up, hitting Southern California, and then certainly our maritime tropical coming off the Caribbean, Gulf of Mexico into the southern U.S. That's a lot better shot. And by the way, if you think about the U.S., I think we're really lucky. Because like I said, this area right along the coast gets lots and lots and lots of rainfall generally. Inland, dry. In fact, the Midwest, quite dry. Southwest, arid, very dry. Well, part of that is because you have this continental tropical airflow coming in here that's very dry off of Mexico. So that makes our Arizona, New Mexico, Southern California, some parts of southern Utah very, very dry. Okay? Very dry. To the bottom of Utah. Okay? Very dry there. We have Gulf of Mexico, warm bathtub, sending up moisture all year long. So if you look, it's wet, dry, and then finally you get here, moist again. Most countries don't have that luxury. They're wet on one side, dry on the other, sometimes arid on this side. We've got the Gulf of Mexico keeping us fed with plenty of water, and if that's not enough, we have some that makes it way for the southern Atlantic. But what I was going to say, there's another really pretty picture of the southeastern U.S., Florida, Cuba. I was going to show you these fronts, and the cold front showed up well, the warm front doesn't. The warm front you see on page 581, the right-hand column. Notice how now the warm air is moving in over the cold air, and that basically the cold air tries to stay where it is and the warm air just forces it over the top, much more streamlined. Notice the size, the height, the intensity of those clouds. They're cumulus clouds, but they don't go up nearly as high. The cold front, those things go up way up there. That's 10 to 15 kilometers in altitude. That would be 6, 7, maybe even 8 miles up. I mean, that's way up there. Whereas in the warm fronts, they go up maybe 3 or 4 kilometers, which is half a mile. So it's not nearly as high. There's a nice little blurb there on urban heat islands. And let me, I know it's time. Let's pick up next time. Y'all remind me how much I've already said about the fronts, and we'll try to minimize redoing them. I think we had warm front, cold front. Don't think we did stationary front, so we're going to start somewhere around stationary front. Okay? And I'll try to hit the urban heat islands, because that is something that's pretty